Now we want to start talking about the chapter 4 of the book, which is titled Multirelational Data and Knowledge Graphs. So far we talked about the approaches that mostly use shallow embedding, and this is going to be sort of a continuation of that. And the next chapter is going to be about graph neural networks and more complex approaches. But one thing that distinguishes this chapter from the previous one is the focus on multirelational data. This time you are not merely concerned with the presence of an edge, but also the type of it. I also encourage you to go back and kind of do a recap on the definitions of multirelational data and different types of examples that we discussed back there. One thing that is critical is that most of the methodologies that are going to be discussed in chapter 4 of the book has to do with the task of knowledge graph completion. Let's go over what exactly this task is. So you have the graph G, which is composed of set of nodes and set of edges. Let me just, in order to be consistent with the notation of the book, write it like this. And then you have particular relationships. And for each particular relation, you might have a tuple such as U, tau, and V being the member of your edges, which basically means that a relationship of type tau is present between the nodes U and V in the knowledge graph. These types of graphs are more commonly referred to as knowledge graphs because, for example, the type of relationship tau can also be associated with the potential fact that holds between the nodes U and V. An example is that U could be a drug and V could be a disease, and the presence of this edge is basically something like, for example, drug U is going to be used in curing disease V, or basically indicating a treatment relationship. Now, the task of knowledge graph completion has to do with predicting missing edges, which is also called relationship prediction. However, there are examples of node classification, etc., defined on multirelational data and knowledge graphs as well. So let's talk about reconstructing the multirelational data. Now, what was the goal as we discussed before? So let's say we have a node U, we have a node V, and a bunch of other nodes. And we have the hopefully low-dimensional representation ZU and ZV. And the goal is to basically be able to reconstruct a relationship between the two. Note that now the difference is that we have multiple types of edges. So when we are discussing the decoder function, in its domain, obviously you need to have the representations for two nodes, but you also have the space of relationships between them. And this is going to be used in order to map this to a value. Now, this output can be interpreted as being related to the likelihood that the edge U tau V belongs to the set of edges in the graph. It is always more intuitive to learn things with examples, so we're going to go over a very basic approach in this domain called RESCOL. And the idea here is that you define the decoder between U, tau, and V to be the basically bilinear product of ZU and ZV. And this is going to be the matrix within. So this matrix is going to be a D by D dimensional matrix. And it's going to be a learnable matrix related to the relationship tau. And then a basic reconstruction loss can be used in order to basically achieve that. Meaning that defining a loss, we want that if we sweep all of the possible nodes and relationships, we basically want to, again, use the normal square loss. We want this decoder value, and we have defined, for example, the decoder as before, and the adjacency matrix that this time includes the relationship as well, and therefore is a tensor, and we want to minimize this sum. So if we open it up again, it's going to be like this. And this would be the loss that we would work with. Basically, if you try to optimize that, it is also very related to tensor factorization and matrix factorization. And it's just something that is worth noting. Next, we want to talk about where exactly was the degrees of freedom that that kind of affected the flexibility of approaches in dealing with different types of problems. So previously we mentioned that the players of this game are decoder, the similarity measure between U and V, and the loss function. And we realized previously, prior to basically attending to the multirelational data, that there are tons of types of defining a decoder and also defining the similarity. Now here in the multirelational domain also there's different types of decoders that can be defined. However, because of the kind of additional layer of complexity that arises from the fact that we now have edge relationships as well, trying to attend to higher order paths and edges would make things more complicated. Therefore, usually in defining the similarity matrix, they base it on the adjacency matrix. So in the case of multirelational data, this is usually what is used as the scoring system. Meaning that because of this complexity, you are more concerned with the immediate neighbors that are kind of, apparent from here. We mentioned that given the fact that the similarity in the context of the multirelational data is often related to or based on the adjacency matrix, the two key components are the decoder and loss. Now here, there are several issues with the previous very simple loss that we mentioned. So we previously mentioned that, for example, if we assume that the decoder is this, one simple loss could be defined like this. Now the question here is that what are the main drawbacks of using something like this? Maybe take a moment to think about this. Well, to understand this, the most important component is basically this part. You can see that, in terms of the order of operations, this is the square value of the number of nodes, or the cardinality of the set of nodes, times the cardinality of set of relationships. However, we often want something that is of this complexity, because usually the graphs are pretty sparse, meaning that the number of edges is very, very smaller than this value. And it will be extremely inefficient computationally to try to target this loss. Now this was the first problem. The second problem is the fact that we are kind of often working with binary values when it comes to the adjacency tensor. Now, mean squared error that is here is often used for regression problems, not for classification problems of sorts. And in this case, we are kind of talking about the presence or lack thereof related to a specific relationship between two nodes in the multirelational graph. Therefore, it might make more sense to kind of work with the losses such as cross entropy that are more focused on that, and that is what we are going to do. So the first instance of these types of losses is cross entropy with negative sampling. For example, this is a definition of this loss. For every edge in the set of edges, you have this component minus, and note that all of these are in the sum. This means sampling negative examples that might also depend on you, sampling negative examples for the tail node of these edges. And then for these, obviously, we want to have this time with this sign, with the negative sign. And essentially, this is the loss that we are going to have. Now note that sigma here is the logistic function, and which can be also defined like this. If x approaches infinity, this value is going to approach 0, therefore it's going to approach to 1, and the otherwise is going to approach to 0, with the 0 being at 1 and at 1 divided by 2. So having this, looking at these relationships, one thing that is kind of understandable is that, so we know that this part refers to the edge u tau v, which exists. Now, therefore, we want this similarity. So we basically want this decoder value to go higher. Therefore, the logistic function applied to it is also kind of related to the probability or likelihood of the presence of u tau and v. And in this case, this goes up. And look at when we were talking about the negative log function, we have something like this. So we want to minimize the loss. So in order to minimize this term, this value should be high. Therefore, we go in this direction on the loss. Now in this part, we are going to sample a bunch of points and a bunch of nodes, and we will talk about how to do that or what kind of common strategies exist for doing that. And there is this coefficient here as well to kind of tune things. But the thing is, we do this negative examples, and for these negative examples, we basically want this value not to be too high, because for example, if this decoder output becomes too high, this value becomes too low, which in this graph basically means that this output of the logistic function is going to go all the way very close to 0. So this thing is going to approach 0. Therefore, applying a minus log on this is going to be very high. So when the objective of the optimization is to minimize the loss, we don't want that. So when we have log of applying the logistic function on the decoder output of ZU, tau, and ZV, this is basically the log likelihood of we predicting true for that edge to belong in the set of edges. And the whole loss would usually be approximated using Monte Carlo approximation. And the probability of negative examples for no use usually basically sample a small set of nodes that are going to comprise negative examples. Now a question and point about the negative examples is how exactly do we do the sampling in order not to end up having a very complex model. One thing that usually happens is that they assume that basically you can consider a uniform distribution over all of the nodes in the graph. That means that there's also a high chance that, for example, you pick a node as a negative and it actually ends up being a false negative, meaning that the node V that you pick, there is actually a u tau V node in the set of the u tau V edge in the set of the edges of the graph. And some methods try to basically do it in a way that these false negatives are minimized or not happening. And some methods basically look at the edges that, based on some prior domain of knowledge, are not going to be there, and then they focus on these types of approaches in order to sample the negative examples from. For example, the book mentions if you have groups of nodes, humans and a group and basically a relationship such as manufactured by, you're not going to find related edges in the graph. So that's going to comprise like a good foundation for sampling negative examples from and things like that. One other thing to mention is that when we're talking about these types of edges, the negative sampling is, in our discussion so far, has been focused on the tail node, which kind of induces a certain bias, and it's also better in some cases to do this on the head node as well to have like a better measurement. One other thing that is kind of very used in multirelational node emitting domain is the hinge loss or the max margin loss. So you have these edges. You also have the negative examples for U. Now what you want, and this probably will remind you of things such as, for example, triplet loss or contrastive loss and things like that. You have this for the positive example, this for the negative example, and you also have delta. How to read this exactly? It means that when you consider, in any case that you have like an edge and so you basically have a node U, you have another tail node V to which there is a relationship tau between U and V, and you have this Vn, which is here, between that and Zn there doesn't exist a relationship. Now the idea here is that if this value here is at least delta value larger than this value, this part becomes 0, and therefore it's it is good enough in some sense. But in other cases, it's going to be incrementally larger, and it's going to make things more complicated, and therefore the loss has to be minimized in order to have a good decoding mechanism. Now we mentioned that that when it comes to multirelational data, the similarity usually is based on the adjacency matrix. However, there are again a variety of methods that you can use to define the decoder. The first thing, and the only thing that we discussed so far, was the RESCOL decoder, which was defined like this. And we mentioned that this is a D by D matrix. And we had two D-dimensional representations for node U and V. Now, one problem with this is the new cost of basically representing the relationships. So for nodes, we have basically D parameters in some sense. For for types and relationships, you have D2 parameters. So that is, this order compared to this order is larger. Now, generally, we are interested in having something like OD in terms of representing the tau. So let's first talk about translational decoders. So one popular class of decoders, as it is mentioned by the book, represent relations as translations in the embedding space. What does that mean? It means that first you define the decoder ZU, tau, and V like this. This is, by the way, from this paper, otherwise known as the Trans-E model. And the idea is that you're going to have this value as the decoder. Now, in this approach, the representation of the relationship is also from RD. Now, what does it mean? So, assuming that, as expected, we want the decoder output to be related to the probability or likelihood of the presence of the edge U tau V, we basically mean this. If you have ZU in the embedding or in your semantic space, and if basically translating this using R tau takes you to the representation for the node V, this means that this value here is going to be smaller. And since the entire thing is negated, this means that the likelihood is going to go up. So this relationship of ZU plus R tau being close to ZV basically guides what exactly the decoder output should be. Now, Trans-E is one of the main baseline applications in the multirelational data domain, and is also one of the earliest approaches that had to do with the dealing with the multirelational decoders. However, this has the drawback of being simple. And the earlier methods basically try to kind of build on top of this and try to make it more complicated. For instance, there's Trans-X model. What it does is that you define the decoder like this. This means that for each relationship and for different head and tail, you're going to have a different function or mapping that applies on ZU and takes it to G1 tau and ZU and G2 tau and ZU. And again, then you will have the trans E model run on that. And G1 tau and G2 tau are going to be trainable as well. Then there's the trans edge model that defines the decoder like this. So again, you have that translation, except that this time you kind of push these embeddings into a better point with using the WR. Another approach is the Multilinear Dot Product, which is defined like this. And again, sorry, this is going to be the decoder value for this. It's going to be defined as the multilinear dot product, which essentially means that you go over all of the dimension elements. It's kind of a generalization of the inner product. So you take the ith element from from ZU, the ith element from ZV, and the ith element from R tau, and you sum over all of those, and that becomes your decoder output. This is often called dist mult. Now this has a serious limitation that maybe pause the video and see if you can spot that. This limitation is that in multirelational graphs, most of the times we have like directed edges and things like that. But this decoder here, defined this way, is symmetric, meaning that if you do, let me write it like this, in dist mult, you would have this be equal to the case in which V is the head node. And this is a serious limitation. Using complex numbers, a method called complex is going to define this decoder output differently. So the way it's going to define this decoder output differently is that this time for ZU and ZV and R tau, we have complex numbers. So previously we had RD, now we're going to have CD. Now we have complex values. Now you define the decoder as the real element of the multilinear dot product of ZU, R tau, and ZV conjugate. Now this is going to make this asymmetric. Now another approach called rotate defines the decoder as this. In this case, this is a Hadamard product. Traditionally, in rotate, they add this assumption that every element in RT is essentially has the magnitude of 1. Now this restriction means that the ith element of R tau can be defined like this. And this means basically a rotation in the complex plane. And that is where the name comes from. So again, if you have like the real component, an imaginary component, given the fact that you want the norm to be 1, you are looking at different ratios on this circle. Now, a critical question is what kind of properties of the decoder functions is actually important for us? The first thing that we want to discuss is symmetry and anti-symmetry. Symmetric means that if this edge exists, we can also deduce that the other way around exists. Now, anti-symmetry means that if the relationship tau exists between u and v, you can say that it's not going to exist between v and u. Now, for example, dist mult that we discussed that use multilinear dot products cannot model this, and it can only represent the symmetric relations. Now, for example, if you go and do the trans E, you can see that decoding here of ZU and tau and ZV. If you want to see if whether or not this is going to be similar to ZV, tau, and ZU, you can easily see that and this basically means, this is V. This basically means that minus R tau is going to be similar to R tau, and this means that R tau is going to be 0, and that basically models the anti-symmetric relationship. The other thing which is closely related to the definition of symmetry is inversion, which means that if relationship tau 1 exists between u and v, it's the same as having relationship tau 2 between u, v, and u. Again, dist mult is something that cannot model this. And the third thing is compositionality, meaning that if you know that tau 1 exists between u and v, and tau 2 exists between v and y, this means that tau 3 exists between u and y. So this is possible with, for example, trans E by defining R for tau 3 to be, using basically the transitivity of the translation. You can see, you can have that. And for RESCOL, for example, you can define this, and you can have that manifested. And here is an important table about this. So going over to, for example, symmetry here, we can see trans E is the only one that is not symmetry. And anti-symmetry, we can see that again, dist mult is going to have problems with that. For inversion, trans X and dist mult. And for compositionality, we know that trans E can do that, RESCOL can do that, rotate can do that, and these three other methods cannot. And in practice, the choice of decoder also has a lot to do with the application at hand and the implications that come from the domain knowledge as well.